Hello everyone, good afternoon to all of you. So today I am going to teach you some topic, point set topology. Okay, so before when I am going to start, I am teach you some last topic, that is our Cantor set. Okay, so hopefully you will be tuned and now continue. I am going to teach you after I am teach you this Cantor set topic. Okay. So first thing is that what is Cantor set? So Cantor set is nothing but it is a famous uncountable set. Okay. Yeah. Hold on. Something related to this topic. I am teach you some related some concept about this Cantor set. Okay. So before we study this Cantor set, one thing is that it means ki if you have some product or it may be some like this. Before I am going to teach you, I have some example. For after this example, then I am show you what is Cantor set and next one is point set topology. So here is some discussion about some Cartesian infinite times Cartesian product. Okay. So here is some discussion about which type of discussion. Discussion about on infinite times Cartesian product. So you know it very well what is infinite. Infinite means if you have some given product and if you have some given sets are tends to infinite, then how to this discussion approach and solve the many problem. So regarding this discussion, here I have some set, okay, at n times. So let a1, a2, a3 goes up to a, okay, are sets. Then what about this? If you have their product and set from I to infinity, and element here a1 cross a2 cross a3 up to an, these kinds of element you have. Okay, so first thing is that what is comes in your mind. So regarding this discussion, I am say about some infinite times Cartesian product, how to approach and how to solve this. Okay, so these are the only consideration. Here I am considered some set and here the infinite Cartesian product of these sets. Okay, now move on how the behaves like this. So if you have Cartesian product from I tends to from I to infinite of a, then you first this kind of observation you got. Okay, so from First observation, all AIs are finite. Okay. Second thing is at least one AI is infinite. And lastly, each AI is infinite. So, when AIs are finite, then two things. First one is at least one AI is empty. Second thing, all AIs are non-empty. Okay. If all AIs are non-empty, then these two information we observe. First one is only finite number of sets has more than two elements, then their product from I is equal to from I tends to infinite equal to finite and non-empty. And second thing about all AIs are non-empty, then so second thing in this infinite number of sets having more than two elements, then their product from infinite I is equal to from 1 to infinity AI is equal to uncountable. Okay. So if you have some product and product like this, if I from I wants to infinite, I'm talking about AI. Okay. So if at least one AI is infinite, then only finite number of sets are countably infinite, and other is finite set. . 。  . 。 . 。 . 。 . 。 . . . . . . . . 。 . 。 . 。 . . 。 . . . . . . . . . 。 。 。 . . . . 。 。 。 。 . . . . . . . . . . . It means कि if you have some product from I is equal to 1 to AI, which is equal to countably infinite. Okay, so this kind of information you got if you have some infinite set of Cartesian product, then if at least one AI is infinite, then two observation. First one is only finite number of sets are countably infinite, and the other is finite set. It means that their product of Cartesian sets from I is equal to 1 to infinity is countably infinite. And lastly, in this case, which case at least one AI is infinite, then second case is at least one is uncountably and other is non-empty. Then their product of from infinite I is equal to from I to infinity AI is equal to uncountable. Okay. And lastly, if each AI is infinite, so nothing else. So these are the basic observation about this. If all AIs are finite, then we talk about these kind of things. At least one AI is empty, and all AIs are non-empty. In all AI are non-empty, then we discuss about these two cases. First one is only finite number of sets has more than two elements, then finite and non-empty. And second thing is if a finite number of sets having more than two elements, then their Cartesian product is uncountable. And lastly, we talk about at least one AI is infinite, then at least one AI is infinite, then only infinite of sets are countably infinite and other is finite sets, and their product AI is countably infinite. Second thing is in this case, at least one is uncountably and other is non-empty, then Cartesian product of all sets are uncountable. Okay, so these are the basic observation, and each AI is infinite is last one. So in this case, something you got new things about you if you have some discussion in infinite times Cartesian product. So this kind of discussion we got. Okay. If you have some infinite kind of Cartesian product sets you have, then we talk about like this. So come to the topic. Okay. So my today topic is Cartesian product and some point set topology. So yeah, here is Cantor set. Sorry, not Cartesian product. Here is Cantor set. So, what is Cantor set? First thing comes in your mind, na? What is Cantor set? So, I am saying you a Cantor set. Here is some discussion about this. Okay, because here we will wait a minute. In Cantor set, we discuss something like new. I think my pen is not clearly visible. So here we will discuss is very famous uncountable set known as Cantor set. Okay, so how you got this? So now I'm going to explain this. What is Cantor set? Okay, So here I'm going to teach you some more problem and before discuss it. Yeah. So what is Cantor Set? Cantor Set is just like nothing. Here we will discuss the very famous uncountable set. This known as Cantor Set. Which kind of set is it is? It is uncountable set. Okay. So according to Cantor set, every real number can be represented by ternary expression. So ternary expression and expression, the ternary expression in this case use digit like this: 0, 1, 2 and all. And by binary expression use digit 0 and 1. These are ternary expression. Okay. So here is some ternary scale and in ternary scale, which means if you have some input like this, x is equal to 0, a1, a2, a3, which means what? Which means x is equal to a1 by 3, comma a2 by 3 square plus a3 by 3 square. Okay. So these are kind of a scale, ternary scale. So here a1, a2, a3, dot dot dot, takes any value. Okay, takes any value between between 0, 1, 2. Respect for number like 1 by 3, 2 by 3, etc. Okay. So these are basic ternary expression. I mean, where is the, hold on. Yeah, here is some expected for number like 1 by 3, 2 by 3. These are ternary expression. Okay. So ternary expression of real number is unique. So write in point format. Yeah, here. So what? Ternary expression of real number is unique. Okay. So now consider the closed interval 0 and 1. Here is some 0 and here is some 1. Now the value is 1 by 3 and second thing is 2 by 3. And here 0 bar, 1 bar and second thing is 2 bar. Okay. So for first 0 bar, which is equal to 0 comma 1 by 3, 1 bar, which is equal to 1 by 3 comma 2 by 3. Okay. And lastly 2 bar, which is equal to 2 by 3 comma 1. Okay. So these are the remove open middle third, and now remainder like this. If you have some set you got from this observation, then first thing is that remove open middle and third remainder. Okay. And first thing is that f1, which is equal to 0 comma 1 by 3 union. New things is that here you basically you find here union for these two sets, and you hopefully you understand the ternary expression. So now consider for a closed interval only here. So we consider two closed interval here. First thing is 0 comma 1 and there look like here you look now. So these are the kind of, if you have some set and you take like f1. So here is the interval for this 0 comma 1 by 3 and second thing is 2 by 3 comma 0. Okay. So how you represent in case of ternary and how you represent in case of number line. So here you maybe write like this for f1. First interval is 0 comma 1 by 3. So you represent like this. Here is 0 and here is 1 by 3. So first thing is 0 and second thing is 1 by 3, and from first and second, first one is 1 by 9 and second thing is 2 by 9. Okay. So these are basic observation. So first thing is you got union na? So union for what? Union for this kind of closed interval 1 by 2 by 3 comma 1. So now put here 2 by 3 and here is 1. So the nearest number you take a infinite number between this na? So take first one is the 7 by 9 and second half is 8 by 9. Okay. So remove open middle third here already you got and move from F2. So what you got for F2? Here is for F2. You got first thing is 0 comma 1 by 9 union 2 comma 9 upon 1 by 9. Okay. And union here is 2 by 3 comma 7 by 9. And lastly union 8 by 9 comma 1. Okay. So these are continue your observation. So here is continue in this fashion. generating a sequence of sets. Okay, so Fn, where f n plus 1 is obtained. Okay, from Fn by removing open middle, third of the disjoint close interval of which Fn is composed. So next thing is we define Fn is composed. Okay, so we define, so if U which Fn is composed, then we define for which Fn is composed. So here we define Cantor set, we define Cantor set K as K is equal to union from I to infinity Fn. Okay, so each of the sets Fn is non-empty, closed and bounded. So these are the kind of some Cantor set. Okay, so hopefully you understand this. Now the some properties related to Cantor set, and what is the property related to Cantor set? Here is some property about Cantor set. So properties of Cantor set. So first one is Cantor set K is perfect. And perfect for what? If it is perfect, then K is equal to K prime. And second thing is Cantor set K is non-dense. And other things is Cantor set K is non Denumerable, it means uncountable. So these are the property of Cantor set. In above, we discuss about Cantor set. Now, lastly, if Cantor set, I am asked about K for binary expression and for ternary expression. So, lastly, Cantor set K. First thing is for and second for ternary expression. For binary expression, you may be write like this: summation infinite, I tends to infinite, ai upon ai upon 2i, where ai is equal to 0 and 1. And second thing is infinite from I to infinite, ai upon ti, where ai equal to 0, 1 and 0, 1 and 2. So these are two cases. First one for we discuss about here. I discuss about here. First one is binary expression, and second thing is for ternary expression. Now move on the main topic of today class, that is point set topology. Okay, so here is point set topology. So what is point set topology? Points in this section, we will study about the concept of something like neighborhood, points, interval, limit points, open, closed sets, and some most fundamental theorem of real analysis. Okay. So now first thing is move on for bounded set. So what is bounded set? So in case of bounded set, here is some issue. Yeah. So the pen is not clear visible, so I'm used black one for my today class. Okay, so the Cantor set is complete. Now today I am going to this time. This is very important topic for basic fundamental of metric space, either it is topology or any real part. So funda is that if you study this, then you may be idea about some what is point set topology and something new. So today class, my aim is to discuss you point set topology. So in this case, in this segment, point set topology, here is some, don't mind if a spelling is mistake here. Okay. So what is point set topology? So first thing is I am asking about what is bounded set. Okay. So bounded set is nothing but if you have some, now I am start with some example. Take a here take some set of natural number, okay, and you have some observation. First thing is for M and second thing is for capital M. And what is this? This is interval. Now take a one line. Here is M and here is capital M. Okay. So in this case, if let some S be a non-empty, S be a what? S be a non-empty subset of R. You may be write like this. S is a non-empty subset of R. Okay. And then we say that S is bounded if there exists M and capital M belongs to R, such that you may be write like this. M, here is some interval X and it is capital M. Okay, for all X belongs to S. So here M and capital M is unknown, okay, and may be called as lower and upper bound. Maybe you may be like this. You say that M is lower and capital M is upper bound. So in this case, bounded set is only things. I have some note about bounded set. So first thing is two or three things here. If M is, if lower bound is known and upper bound is unknown, then what observation you have? Which kind of observation you got here? So for this explanation, if M is known and M is capital M is unknown, then this is called bounded below. Okay, it is called as bounded below. Bounded below and unbounded above. Hence, S is unbounded. If a lower bound is known, then bounded below and unbounded are upper bound maybe. So maybe say that it is unknown. So unbounded bound, hence S is unbounded. That is, if you have some example like this, S is equal to set of natural number and element here 1, 2, 3 and 4 types. These are the kind of element where M is equal to 1, okay, and capital M is unknown, okay. So these are the kind of some note about when if M is known and capital M is unknown. Now move on second part. So second thing is one more note about this. If a small m is known, then S is unbounded. Okay. If M is known, then S is unbounded. Then what observation you got? You got like if M is known. Sorry, here M is known and then S is unbounded. So you have some element like this. That is, here is some example about this. That is, S is equal to the kind of element R comes like this: -1, -2, -3, and -4 types of element are come. So clearly say that M is equal to N, M is equal to 1, and a small m is equal to unknown. Okay. So these are the kind of some note about if M is known, then S is unbounded. Those this kind of observation we got. Now next thing is one more note. Here, if both a small n and capital N are unknown, then we say S is unbounded from both sides. That is, S is equal to the kind of element you put here. Z is equal to, and their entries are -3, -2, -1, 0, 1, 2, 3. Okay. So here is some note about this. Bounds of sets are infinite in number. Okay. So these are the kind of some example. Now move on the next part, that is supreme of set and infimum of set, which is very popular and every time asked in different exam. Okay. So now next topic is supremum and of a set. Now move on the supremum of set. So what is supremum and what is infimum of a set? First thing is that if you have some line, okay, so here is some element and here is some element. So maybe say that here if you have some element, then existing here the some infinite type of elements are present here in this interval. And in this case also infinite times of elements are present here. So maybe say that here is some point which is very less. It means key may be called as supremum or may be called as infimum. So at least here I am say you some observation. If the least upper bound of a set S if exist is called supremum of that set. The least upper bound of a set S X is exist. Hold on. So the infimum of that set That is, it is set of all lower bound of S and largest number of say M, then M is added called as GLB. So I think maybe Mary light comes over my face. So needs to use black one for best explanation. Yeah, here is I am right here, supremum of a set. So what is supremum of set? So the supremum of set may be called as the list upper bound means LUB of a set S if exists is called supremum is called the supremum of that set. That is, if the set of all upper bound upper bounds of a set S called set S as the smallest. I think in this lecture is some big issue because I am writing something and it will down and something not clearly visible. So sorry for that. Okay. So here is some, if in this case, supremum of set, the least upper bound of a set as if exist is called the supremum of that set. That is, if the set of all upper bound of a set S has a smallest number, say M. Say M, then M is called least upper bound or supremum of S. Okay. And here is some note about this. So now set S is very closely related to the set S, that is, if supremum of S is equal to capital M, therefore imply for all x belongs to S and x is greater or equal to M. Okay, so for any epsilon is greater than 0, there exists T belong S such that T is greater than M minus epsilon. Okay, so that is if we subtract a smaller and a smaller value epsilon on supremum S, then there is one element in S which will be M minus epsilon. Okay. So these are the kind of some supremum of a set. Okay. So what is supremum of set? So supremum of set is the thing if you have some set and in set you have suppose that you have some interval 0 and 1. So less interval is 0 and upper is 1. Okay. So least upper bound may be a set as if exist is called, it means what? Least upper bound if exist, then called a supremum of that set. That is, if set is all upper bound of a set S has a smallest number, say m, capital M already I am told you, na? Then m is called a least upper bound or supremum of that set. Okay. So here is some note about supremum of set. So maybe closely related to the some set, given set, if supremum of S is equal to capital M, so for all x belongs to S and x is less or equal to capital M, for any epsilon is greater than 0. So there exists t belongs to x is that t is greater than m minus epsilon. So that is if we subtract a smaller and a smaller value of epsilon for S supremum of S, then there exists one element in S which will be greater to m minus epsilon. Okay. So next thing is infimum of a set. Okay. So in this case, the greatest lower bound GLB, you maybe not use short form, only use greatest lower bound of a set S if exist is called the infimum of that set. That is, if the set of all lower bounds of S has largest number, say small m, then a small m is called GLB or infimum of S. So again, here is some note. What it means, first I'm telling you what is infimum of a set. So if you have some interval are already given, the greatest lower bound of set S, if exist, okay, then called as infimum of that set. That is, if set of lower bound of S has largest number, say m, then which is called as infimum of a set. Only this. Here is some note about related to this. So note. So infimum of set capital S is very closely related to set S, that is, if infimum S is equal to M, therefore imply for all x belongs to S and x is greater or equal to small m. So for any epsilon is greater than 0, so there exists a t belongs to S such that t which is less than m plus epsilon. So these are the kind of something infimum of a set S is about this. What it means? It means that is if you have some infimum of set S which is equal to m. So therefore imply some element x belongs to S and x is less or equal to small m for any epsilon which is greater than 0. So there exists T some second element which is also belongs from that set says that T is less than m plus epsilon. So that is our infimum of a set. Now I have some more note about this infimum of a set. Not only infimum, only both are combined here, supremum and infimum both. So supremum and infimum of a set are always unique. Always unique. So let set S is bounded. Therefore imply that there exists a small m and capital M belongs to R such that M is X and capital M for all X belongs to S. As no bounds are not unique, then then infinite is number. Okay, now move on next slide. Okay, so let T1 which is equal to collection of all upper bound of S. S, okay, that is T1 which is equal to X belongs to R so that X is greater or equal to small m. And second thing is, and for T2 which is equal to collection of all lower bounds of S that is T2 equal to such that X which is less or equal to a small m. Okay, so from T1 and T2, it is clear that capital M and a small m are the smallest. And the largest element of T1 and T2 respectively, and hence they will unique. Okay. And second thing is that one more note. First, what is this? First, I am say about this. Here I am only write supremum and infimum of set R so that here I am show you supremum and infimum of set are always unique. So how you prove that? First thing is consider one set which is bounded. Okay. If it is bounded, then here exist two cases, upper bound and lower bound also. So here upper bound and lower bound are exist for all x belongs to set S. So you know that are not if they are not unique, then infinite is no. So here is two cases are. First thing is for consider one is for if let T1 is the collection of upper bound of S. If S is the upper bound of S, that is T1 x belongs to R, where x is less or equal to capital M. Unknown, na? It is known na already before. If you have some set and have some upper bound of set S, then may be considered here T1 which is equal to x belongs to R, such that x which is greater or equal to capital M. And second thing is for T2 collection of all lower bound of S, that is T2 which is equal to x belongs to R such that x is greater or equal to M. Do things first for one upper bound and second case for lower bound. So here we see that here exists small m and capital M are both, then we say that it is a bounded. So from T1 and T2 it is clear that M and capital small m and capital M, the smallest and largest element of T1 and T2 respectively, and say that it is unique. Okay. So next note I'm going to teach you here. Bounds of set may or may not be belongs to the set if they belongs to the set called largest and smallest element of that set. Second thing is S is equal to n plus 1 by n, comma n belongs to natural number. Here element are -2, -3 by 2, -4 by 3, -5 by 4, comma dot dot dot. So supremum of S, which is equal to -1, does not belongs to S. And second thing is infimum of S is equal to -2, which is belong S. Okay. So here, if bounds of set may or may not belongs to the set, if they belong to the set called largest and smallest element of that set, first thing is, maybe you maybe understand this, na? It means कि if you have some bounded set, may or may belongs to the set, okay? May or may not belongs to the set. If they belongs to set which is called as largest and smallest element of that set. So from first say that if you have some set, here is lower bound is 0, which is does not belongs to S. When put here 0, then it is infinite, okay? And if the upper bound is 1, so it belongs to set S. And second thing is like this, okay? So these observations show you if they belongs to that set. So you maybe say that it is called as largest and smallest element of that set. So now I have one more result about this whole fondant set suprema infimum of a set. Okay. So the results say that first one, every bounded set, every bounded subset of R has supremum, infimum in R. Second thing is every subset of bounded set is bounded. And third thing is every finite set is bounded. Every bounded set, every bounded subset of R has supremum and infimum in R. Every subset of bounded set is bounded. And third thing is every finite set is bounded. Okay. Now, one more note. Note say that subset of an unbounded set is not necessarily unbounded. That is, R is unbounded. But A comma B contain R is bounded if A and B are finite. Okay. So here is result about some bounded and unbounded. So first result say that every bounded subset of R has supremum and infimum in R. Okay. Second point say that every subset of bounded set is bounded. And third point say that every finite set is bounded. So lastly, what your observations say that here my observations say that every bounded subset of R has supremum and infimum. Okay, note say that subset of an unbounded set is not unnecessarily what unbounded. That is, if R is unbounded but A comma B contain R is bounded if A and B are finite. Okay. Here some phone are coming. Wait a minute. Yeah, I hope maybe it is unmute. So I am going to teach you some result and some note about the case of in case of bounded and unbounded. Okay. So here is note about subset of an unbounded set is not necessarily unbounded. That is R is unbounded, but A comma B contains R is bounded. If A and B are finite, okay, if A and B are finite, then we say that this. So now one more note. One note say that every infinite set need not to be unbounded. That is S is equal to X belongs to R and in case 1, X and 3. So is infinite but bounded by 1 and 3. Hold on, one more phone is coming. So So here say that every infinite set need not be unbounded. So first thing is if x is equal to x belongs to R1 is less than x and less than 3 is infinite, but bounded by 1 and 3. So if bounded by 1 and 3, that it is only node. Here is one more observation. The point is 4. If U is an upper bound of a set S and U belongs to S, then U is equal to supremum of S. Okay. And in fifth point, if L is a lower bound, L is lower bound of a set S and L belongs to S, then L is equal to infimum of S. Okay. And 6 point, every non-empty set of real number which is bounded below has the greatest lower bound. Okay. And I have many example about some supremum and infimum. First, in this case, if U is an upper bound of a set S, okay, what I'm trying to say you, here is one more note about, say that infinite set, okay, need not be unbounded. So take a one example and their interval is 1 and 3. So infinite but bounded by 1 and 3. Second thing is if U is an upper bound, here the notation U is an upper bound of a set S and U belongs to S, then U is equal to supremum of S. And second thing is if L is lower bound of S, set S, then L belongs to S and L is equal to infimum of S. So here every non-empty set of real number which is bounded below as the greatest lower bound. Okay. Now move on to next part. That is one most important. The points are A points here. First one is supremum of A plus B, which is equal to supremum of A plus supremum of B. Okay. Second thing is supremum of A minus B, which is equal to supremum of A minus supremum of B. Third thing is infimum of A plus B, which is equal to infimum of A plus infimum of B. I am audible now? Okay. Yes, clearly I am audible. And fourth point, say that supremum of A union B, which is equal to max of supremum of A, comma, supremum of B. Okay. And for fourth point, fifth point here, if not A, here infimum of A union B, which is equal to mean of infimum of A, comma, infimum of B. So you are getting my point. These are the important observation. Okay. And here A plus B, which is equal to A plus B. Okay. And A belongs to A, comma, B belongs to B. And second thing is for A minus B is equal to A minus B. Okay. And A belongs to A and comma B belongs to B. Okay. These are the basic injection. Now next part. Okay. That is point number 9. Okay. So if A is bounded set, not bounded, bounded subset. Subset of R, then lambda dot A is also denoted by also bounded. It means lambda belongs to R, and first thing is that supremum of lambda dot A is equal to lambda dot supremum of A if lambda is greater than 0. Here is the notation that it is lambda. Lambda is greater than 0. Infimum of lambda dot A, which is equal to lambda dot infimum of A if lambda is greater than 0. And third things, supremum lambda dot A, which is equal to lambda dot infimum of A, and if lambda is less than 0. And fourth things is infimum of lambda dot A, which is equal to lambda dot supremum of A if lambda is less than 0. Okay. So these are the kind of some discussion about something infimum and supremum. Okay. Now the time for question part, which is very important. So the question is find the supremum and infimum of set S. Okay. So here is some, I will give you some set. Here is S. An element in this set is sine 1 by n, where n belongs to natural number, which is equal to the when you put here the values of n, that is when you put here 1, and then here is a sine 1 are come, and further you when you put here the 2, then sine 1 by 2, and lastly sine 1 by 3, and so on. You got the value. Okay. So since 1 by n, not 1 by n, so since 1 by n, h lies between 0 and 1, because you know the domain of sine theta, that is from 0 to 1. So sine 1 by n will give its supremum and infimum when n is equal to 1 and at 0 when n tends to infinity. Okay, hence supremum of s, which is equal to sine 1, belongs to s, and infimum of s, which is equal to sine 0, belongs to s, and so on. So sine 1 by n is less and on 0 comma 1. Again the same problem are come. Hold on. Here is 0 comma 1. So these are the two information when you have some value like this n 1 by n belongs to n. When you put the value of n rises up to n. Okay. So 1 by n is lies between 0 and 1 because you know the interval for sine area to domain and something range are 0 and 1 for sine n. Here gives it will supremum and infimum when s equal to 1 and at 0 when n tends to infinity. So hence supremum s, which is equal to sine 1, belongs to s. Now infimum is 0. So you cannot go here the supremum and infimum. So sine 1 by n is monotonically decreasing on 0 comma 1. Now second thing is I'm talk about one more example, that is s is equal to cos 1 by n and where n belongs to natural number. Okay. So supremum of s, which is equal to cos 0, which is equal to 1. Okay. And 1 does not belongs to s. So infimum of s is equal to cos 1, which is belongs to s. And point number 3 here, s is equal to x belongs to r such that x, which is equal to minus 1 to the power n, mapping n, which is equal to minus 3, minus 1, 2, 4, and so on. So here n belongs to natural number. So s is unbounded on both sides, hence supremum of s and infimum of s doesn't exist. Okay. Now next part is Archimedean property. I think in Archimedean property may be discussed in next class. And after Archimedean property, discuss about some neighborhood, adherent point, closure of set, limit, cluster point accumulation, and derived set, and so on. Now, the topic is remain today, but I am explaining quickly fast. Okay. Because when I write something, it take too much time for explanation. And today my aim is to just complete this point set topology full part. Okay. So lastly, I am show you which kind of information I will give you. Here, point set topology are completed and all node supreme of set are also completed. Now the infimum of set are complete and these two parts are also complete. Okay. And here is some result are already complete. Now the one more question is also complete. Now what is Archimedean property? So basically the Archimedean property for any delta which is greater than 0, there exists n belongs to natural number such that 1 by n is less than delta, where for all n is less than m. N is greater than small m. So here the properties say that if you have some delta which is greater than 0, there exists n belongs to natural number such that 1 by n times type of terms are coming which is less than delta. So for all n is greater than capital M. Hold on, the time is maybe 6:38. Needs to send a message in group. Okay. Yeah. Already sent message in group. Yeah, here the Archimedean property say that if you have some delta which is greater than 0, there exists and belongs to natural number such that 1 by n which is less than delta for all n is greater or equal to greater than n, and let for all x comma y belongs to R and y is greater than 0. I mean, next to the time of, okay. So here is our median property, then interval, then open and close, semi-open, and so these are remain and very small topic. Maybe discuss in next class. So thanks for watching these videos because I am getting late for going home. Okay. So thanks for watching these videos. Stay tuned, like, share, and subscribe. Does not forget this, and share with your friends also this content. I will, and suddenly you join my Telegram channel. In my Telegram channel, also the classes are begun naturally in YouTube. My other platform, that is Genie Tutorial. Here, that where I'm discuss about some chemistry part and for only class 10th and 12th. So join Genie Tutorial Telegram channel group, and it is my personal YouTube channel. Okay, so thanks for watching these videos. Meet you in next day.